So sometimes when we're talking about data, it's, if we're talking about those babies' weights, and we had that mean was 3.6, and someone said, oh, I had a baby who was born who was 4.5. What that tells you is it tells you that you're higher than the average, because the mean was 3.6 and your baby was 4.5. But it doesn't tell you, is that crazy? Is that normal? Because what happens if babies' weights had a standard deviation of 8 kilograms, right? That would be really crazy, because that means that 3.6 would be your average. And then if you go up 8 and down 8, okay, we're going into negative baby weights here. It's kind of hard to imagine. They just float when they come out, I guess. And we go up 8, we go up to 11.6, then your baby that was at 4.5 or whatever I said would be like really quite within the normal weights of babies. But what we often want to do is we want to standardize that score, and we use this formula to calculate the Z-score. And what the Z-score is how many standard deviations that baby was. So when we look at 4.5 and we find out that that was 2.1 standard deviations above the mean, then we could say, wow, that is quite a bit higher than the mean, because you're already outside of that 95% of all people, because you're over 2 standard deviations away. So then you would be like, that isn't, not that it isn't normal, still follows a normal distribution, but that's where these words come from. That's not as normal as we're used to, because it's far away from a standard deviation. Okay. So here's a television normally distributed with a mean of 8 years. So chances are that your TV is going to die on you, or that it will not last more than 5 years, are 0.05. We want to find out the standard deviation. So again, we can draw a little picture to see what we know here. It's normally distributed. That means you automatically are allowed to get a bell curve. You know that the mean is 8. Below 8 would be the number 5. And the chances will not last 5 years are 0.05. So when we think of this, what does that refer to? That refers to this area right here. But we don't know the standard deviation. I'm going to draw this same thing out, and I'm going to draw a standard normal distribution. I'm going to draw that 0.5%. Because if I used my first graph, I wouldn't be allowed to use inverse norm. There's not enough information. But if I use my second graph, I could use inverse norm. Now, if I go to my second graph and I go to my calculator, I go to distributions and I go to inverse norm, and I want an area of 0.05, 0, and 1, it tells me that that happens when it's 1.64 standard deviations below the mean, at negative 1.64. That's our Z-score. Now this formula that we just found out to standardize data, you have, maybe we want to highlight this is our z-score. Here's our mean. There's our standard deviation, and our x is an actual score. Wow, that's too many L's in actual. So now we can take this data, because we were able to use inverse norm to find our z-score. And now that we've found our z-score, we have our z-score. We have the actual score is 5. We know that our mean is 8. The only thing in this formula we don't know is sigma, our standard deviation. So we can go back to here and say, well, I can plug everything in. 1.64 equals 5, negative 1.64, because 5 minus 8 over sigma. Multiply both sides by sigma and divide both sides by negative 1.64. And I'll have negative 3 divided by this answer. And I find out that my standard deviation is approximately 1.82. Which means that most TVs, if we make that roughly 2, most TVs should last between 6 and 10 years. And companies will use data like this to say, okay, well, let's make a 3-year warranty on this. Because there's a very, very little chance that it's going to be less than 3 years. And then we won't have to, it sounds good, it gets people to buy it, and we don't have to worry about actually paying any money out on the warranty, because it's very unlikely that that will occur. If they find out that they've got a better product that lasts longer, they can offer a longer warranty and still not have to pay it out. But when you look at 2 TVs and one has a 5-year warranty and one has a 3-year warranty, what do you think? The 5-year warranty is a better TV. So you lean towards that one. So let's decode this question, because it's got all the fancy math print here. We got a random variable x. It's normally distributed, so that's telling us we got our bell curve. What do those 2 numbers mean inside? The first one is our mean, so we know that our mean is 2. The second one is our variance, and they're very kind to write it as 3 squared, because then that tells us our standard deviation is 3. So we can go 1, 2, 3 above, up 3, up 3, up 3, down 3, down 3, down 3. And we want to find the probability that something gets a score of less than 3. So we draw a line at 3, and we're looking for this area here. So the first thing you're going to be asking yourself, is this an inverse norm or a normal CDF question? Since we're finding probability, it's going to be a normal CDF one. It's less than 3, so we're going to start off at negative infinity, then go up to 3, a mean of 2, and a standard deviation of 3. Plug that into your calculator. And what do you get? Anybody have a value? 63.1%. So if we're writing it as 63.1, we're going to write it as a percentage. And, or you could write it as the decimal, 0.631. So there's two more there. I'm going to get you to try them. So try these two. And then this is sort of a recap of today as sort of how to decipher which question is which. You know, if you had a z-score and you're given a probability, you can use normal. Anytime it says find a probability, you're going to use normal CDF. If you're given a probability and you need to find a z-score or you need to find an actual score, that's when you're going to use inverse norm. Sometimes you're going to be given a probability and a z-score and you're going to be asked to find a mean or a standard deviation. You're going to have to use your inverse norm and our formula for z-scores like we did in that one question. That's probably the hardest type of question. This one that we did right here, where we weren't given enough information, we had to rethink of it as a standard normal, use inverse norm to find a z-score, and then use the formula to work your way back to find the standard deviation. So that one, that type of question appears, you're given a probability. Sometimes you're not given that z-score, but you could find it. And then you have to find either the mean or the standard deviation. And of course, there's some practice questions as well.